Hopefully y'all will catch back up and y'all see this part 2 video. Apparently my phone died, so I'll go ahead and try to set it up in such a way where I'm using my iPad. My phone was a much better solution for the time being because of the stand, so I'll try to go from here. So hopefully people will catch back up and see that I went live again. But what I'll do first is try to get it to where it's a wide view on that, and then I'll flip my camera around and then we can kind of see here. All right, so the third law of thermodynamics is stating this. Okay, so that's what we're seeing there. I'm sorry, the total entropy of the universe is increasing, usable energy is decreasing. That's my bad. It's written on the board in just a second, so you should be able to see that once I get this up and running. So let me move back just a little bit, and how does that look? That's not too bad. Okay, I like it. It could be better, but it'll work for now. So I do apologize, as again, I said my video went dead, or my phone went dead, so I had to pull up another one. I'll go respond to the other chats and the messages and try to send them on their way to this new video. So give me just a second and I'll pick back up where I left off. All right, I think we got everybody going up and on. Sorry, it's about 2 minutes. It looks like I've got a couple of people following along with me. Kimberly's back, good. Okay, so now we got this overall usable energy is decreasing, which means entropy or disorder is increasing. If you were to look at your review, it's asking you what the total entropy of the universe is doing and the usable energy is doing. So you would put that entropy is increasing and the usable energy is decreasing. Go ahead and do that real quick, and I'm going to get myself another review so that I can catch back up with you and make sure we're in a good spot. So you have to excuse me, I had to go pull up my review on a different device since my phone died. Didn't prepare for that one, I apologize. I'll get better as I use it more. But I am now looking at number 29. It says work is done by the system, the internal energy of the system does something. Okay, so that kind of goes back to this first law that we were talking about just a second ago. Make sure you take a quick note of this guy, because that's going to help you answer number 34. And we'll talk about that in just a second. But I want to help you answer number 29 now. So I'm going to erase this information so that I can get it. If you needed to pause the video and rewind me, you can have access to do that, or you can go back and watch this video later to do it. So this first law of thermodynamics is stating to change the internal energy, we have to change the Q or the W. If my Q remains 0, the only thing I have now to affect it is the work. And if work is done by that guy, that means it's pushing. And I believe that's what it's asking on number 29. If work is done by the system, then the gas is pushing. So if the gas pushes, then that means this guy's positive, which would make the internal energy decrease because of the equation. So we would see this. If I had a piston like this, and the gas started expanding, then the internal energy of this guy would drop. So we would say this, work done by internal energy decreases. Okay? Any questions thus far? Went out of focus. Okay, hold on just a second. Let me see. There we go. That's a little bit better. Number 28. Number 28 is basically saying the total entropy of the universe is increasing. The usable energy is decreasing. So entropy is increasing, usable energy decreasing. Hopefully that helps you. Now I should be at number 30. We answered already. So you should be at number 32. 32, I've given you the equation to 32, 33, 34. I'll have the equation there for you. What that means is that on 32, you're basically going to say Q is equal to, if I want to change the temperature, the heat transfer of an object, if heat's going to leave an object, it's going to do it like this. If it's just heating up or cooling off, not changing phase. And if it's water, then C, in this case, because it's grams, will be this, joules per gram Celsius. Okay. For this problem, on number 32, they wanted to know what the temperature change was. So you're going to divide both sides by MC. So you should do Q divided by MC, which in this case means that you're going to put whatever your joules was, and your kilograms are going to go here, and you're going to do 4186 there. Now, please make sure that you put this guy in a double, like this guy needs to be multiplied first before you do the division. That is very important. So that'll help you answer that one there. Sonny, what are you talking about, denting the universe? Okay, so there we go. Hopefully that helps you with number 32. Now number 33 is what happens if you're changing phases. So in this case, we're melting ice or water. We'll use this equation where LF is equal to 333,000. You're going to multiply that guy by the mass. That value is, let's see, kilograms, joules per kilograms. Joules per kilograms is the unit. So that kilograms goes away and your answer is in joules. Okay? So that should help you answer number 33. So you got, this guy's in kilograms. It gives you a mass of 300 grams. Divide by 1,000. That means you'll have 0.3 kilograms. And then multiply that number by that number, and you should get your answer. All right, that brings us, we're coming down the stretch here. Number 34. I'm going to just double check in with my questions and see if there's anything that needs to be addressed. Okay, looks like we're good. A couple of views there. Nobody's saying anything. Okay, so I'm going to go ahead and move on to number 34. You answered, this was number 33. This was number 32. So I need to do 34. I'll probably erase 32 so that somebody can get 33 down. If you have to, pause me. Go back and watch it again. All right, 34. We're talking about the second law, thermodynamics there. We're going to do QH minus QC over QH, which means in this case 350 minus 250 over 350. How do I know that? Because it receives 350 and 250 is put off. You do the subtraction there, you should get 100 divided by 350. And if you do that math real quick, you should get a decimal place, something that's less than 1. Because we can't have a 100% efficient engine. So I got 0.29, and there is no unit for efficiency. That leaves us with 35, 36, and 37. I'll finish those questions up. So Kimberly's asking us to go back. So what we got? Okay, so perfect. That's looking good. I can go through there. So I'm going to answer 35, and then we'll kind of finish up for those that need it for 36, 37, and 38. Number 35, when the volume of gas comes compressed without heat transfer, explain why the internal energy goes up. Okay, if we're looking at number 35, okay, if I compress a gas, so I start pushing this guy in, and he gets smaller, and there's gas particles in here, and we move it into here. Now the particles have less room, so the pressure is increasing. The pressure increases. If that pressure increases, there's a direct relationship between pressure and temperature, so the internal energy will start to increase. So what we would say in this case, we didn't put any heat in. We didn't heat it up, but we compressed it. And so it made the internal energy go up because the pressure increased. So we would say pressure increased is the reason why. Why does that happen? Pressure increases. All right, I'm going to move on to the last couple ones there. Number 36, adiabatic is very important. A adiabatic process happens when there's no heat transfer. So we're talking about a process like this where I did not transfer any heat. So adiabatic process Q is 0. There is no heat. No heat. So then the next thing in 37 is asking you Well then, what is a process in which the internal energy might change but no work is done? Okay, well, if the internal energy changes but the volume doesn't change, an isovolumetric process occurs. Meaning no volume change, but heat is transferred. Heat is transferred, causing a change, in internal energy. Okay? And last but not least, you have an equation there. All you got to do is multiply those two. But if I want to find the work, and I have the pressure and change in volume, if I multiply the two, in this case I had 750 pascals, and I'm going to multiply by 10 liters. I should have got 7,500 joules of work. I believe it was 750 pascals. So that here is number 38. Hopefully I answered all of your questions. I know it was kind of all over the place, and we had a second video. I'm just checking in and seeing what else we might have there. If you are missing anything on your packet, hopefully the video will go through any other types of questions that you may have over the final. If you can answer these questions, you're in a good spot. As always, if you want to email me, I should be able to help you with any questions you might have. This video will be available on YouTube once I am done. If there's not any questions, I'm going to go ahead and move on. All right, so I'm going to go ahead and call it quits. Y'all have a good evening. If you're taking the finals, study hard. We'll see you tomorrow. Otherwise, we'll see you tomorrow and we'll take the finals later. Bye.